So you'll actually find that, to me, it makes more sense to do section 3.3 before we do 3.2. So in section 3.3, I'm going to go through some vocabulary that's really important. So we've talked about what an event is. We've talked about how to find the probability of an event. I want to talk about the intersection of two or more events. And that is when two events cross each other. Just like the intersection of two roads. The symbolism that you're going to use is an upside down U. So this is events A and B. And is your key word there. And it is everything in both events, but nothing is repeated. And then the other thing we're going to talk about is the union of two events. And this is everything in one event or the other event or both events. We use an actual U for union. And this would be events A or B. So the key word for intersection is and. The key word for union is or. So I'm going to show you some of the different ways that data can be given to you. And we'll talk about where the intersection is and where the union is. The first thing I want to look at is a contingency table. So this is one way to display data. So let's say we have males and females. And let's say we have blue-eyed, brown-eyed, and other. I'm just making this up, so just kind of bear with me. And I'm going to put in some numbers. So let's say my class had 24 people in it. So the total is going to be down here. So let's say there were 2 and 1 and 3 and 2 and now let me actually make those bigger. Let's go 4 and 3 and 5 and 7 and 2 and 3. So that should give me 7 total with blue eyes. That should give me 12 total brown eyes, which is 19 and 5. So that gives me 24. And 11 males and 13 females, which also gives me 24. So if I said that event A was defined as being male and event B was defined as having brown eyes, then I can answer all kinds of questions. The probability of A would be 11 out of 24. The probability of B would be 12 out of 24. The probability of A and B, so this would be where they intersect each other. So that would be where male and brown intersected each other, which would be 5 out of the 24 people. And if I did the probability of A or B, then that means I'm talking about everybody that is male plus everybody that is brown. But I'm not going to count anything twice. So that would be 4 plus 5 plus 2, which is 11, plus 7, which is 18. Now, if you look at just the total brown and total male, 12 plus 11 actually gives you 23, which is much bigger than 18, which is the correct answer. So we have something called the addition rule. And the addition rule says the probability that A or B happens is the probability that A happens plus the probability that B happens, but you don't want anything in there twice. And since that 5 is added into both the male and the brown, we would not add it twice. So if we were adding the 12 and the 11, we would need to take it out. And that 5 represented the intersection. So the addition rule is finding the probability of the union. So you can either do it strictly by counting off of the chart, or you can use the addition rule that says find the probability of each of them individually, but take out the intersection because it's in there twice. Another way to display data is in something called a Venn diagram. So let's say, and we'll use the same information as above, let's say we had 24 students. We have 11 of them that are male. We have 12 that have brown eyes. And we're not going to distinguish between blue and other. But 12 have brown eyes. And 5 are males with brown eyes. Hopefully, if I say the word Venn diagram, you know what I'm talking about. And that is that you've got a box. And then inside the box, whoops, sorry about that. You have events. And our events are represented by, whoops, circles. See if I can get this circle in the right place. Sorry about that. me try this one more time. Well, this isn't happening this isn't. Okay. So you can tell that we have male and we have brown eyes. We know that there are 24 students. And I'm putting the 24 up here so that I know what everything should add up to. I know that 11 students are male, but this whole circle has got to equal 11. I know that 12 students have brown eyes, but I know that this whole circle has got to be brown eyes. So I have to start in the middle with the 5. So the 5 is the intersection. That's where the two things cross. Then I can figure out what my other numbers should be. I know that this whole circle's got to be 11. I already have 5 people accounted for, so that means that there are 6 males that don't have brown eyes. Then I know there are 12 people that have brown eyes. 5 of them are already accounted for, so I know that there are 7 more people with brown eyes that are not male. That accounts for 18 people. So there are 6 people, and those 6 are neither male nor have brown eyes. So the key in creating a Venn diagram is you always have to start in the middle with the intersection. And then the total male is 11, so I had to subtract 5 from 11 to get 6. The total brown was 12, so I had to subtract 5 from 12, and that's where the 7 came from. Then I added up what was there, and that was a total of 13. A total of 18. And I subtracted the 18 from 24, and I had 6 left over. And that goes still in the box, but not inside either of the circles. So that's another way to use a visual display to answer questions about data. So if I wanted to just look at a Venn diagram with 2 events A and B, and I wanted to look at the intersection, that would be A and B. If I wanted to look at the union would be everything in both circles, including the intersection. Now, there's something that is also called mutually exclusive events. And they are events that do not intersect. So if there is an intersection, then they are not mutually exclusive. If there is not an intersection, then they are mutually exclusive. So that kind of takes you through section 3.3, given those new definitions. And now I'm going to go back to section 3.2, which is conditional probability. Conditional probability is the probability an event will happen Now here's the key. Given that another event has already happened. So if we look at the contingency table up here, let's see, 452, 373. I'll draw that again. I can, instead of talking about being just male or being female or having brown eyes, I could talk about the probability of being female given that the person has blue eyes. Well, once you are given something, what that does is it minimizes the sample space. So you'll notice in section 3.3, when we did these problems, everything was out of 24. It was out of everybody. But once you know something has happened, then you minimize the sample space to what is given or what is known. So if I know they have blue eyes, then I am now only talking about these people. So in this case, I'm only talking about 7 people. The way that this is written is the probability A happens given that B has happened. So this is the probability A happens given that B has happened. So in this case, it would be the probability they are female given that they have blue eyes. And we can look and see that we're now talking about 7 people. And out of those 7 people, there are 3 females. But where did these 3 and 7 come from? So let's look at that. There's a formula that says the probability that A happens given that B has happened. Well, where did the 3 come from? The 3 is actually where the blue and the female intersected. So that's the probability they both happen, or the intersection, out of, well, what was the 7? The 7 was the total blue. And blue was what came after the given part. So the intersection out of the given, and this is the conditional probability formula. based off of this formula, if I just do simple arithmetic and solve for the intersection, I get something called the multiplication rule. And the multiplication rule says the probability that A happens and B happens is equal to the conditional probability times the probability of the given. Now, once we start working out problems, this is going to make a whole lot more sense. But here's an example. If I want to talk about the probability in my last experiment of rolling a die and flipping a coin, the probability of getting a 6 and a tails, which is the intersection, that would be the probability of 6 and tails equals the probability I got a 6 given that I got a tails times the probability that I got tails. Well, in this case, because the roll of the die and the flip of the coin are independent of each other, they don't have anything to do with each other, it doesn't matter that I got a tail on the coin. That's not going to affect whether or not I got a 6. So in this case, that's just going to be the probability I got a 6 times the probability I get tails, which would be 1/6 times 1/2, which is 1/12. And if you go back to the actual sample space from the last section of rolling a die and flipping a coin, there were 12 outcomes, and one of those was a 6 and a tail. So that kind of shows you how the multiplication rule goes to back to the whole idea of the intersection and the sample space. One more thing to go along with this is the idea of with and without replacement. Because you're going to see some problems, like when we're drawing 2 cards. And if we draw 2 cards, the probability is going to change if we keep the first card out. So with replacement, means you draw a coin or draw a card or flip a coin or draw a marble, but the first item is replaced before the second is drawn. Probability of success does not change. Without replacement, the first item is not replaced. When the second is drawn. And so probability of success does change. So here's an example, and this should help make a whole lot more sense. I'm going to draw 2 cards. Obviously, you need to know how a deck of cards is made up. You have 4 suits. You have 13 cards in each suit. And every time you do a problem for me with cards consider aces a face card. So you'll have number cards and face cards. So if I draw 2 cards with replacement, and I want to know the probability, the first card is a king, and the second card is another king. Well, the probability that the first card is a king, there are 4 kings in the deck and 52 cards in the deck. That would be 4 out of 52. This goes back to the multiplication rule. The second card being a king, well, if I put the first one back, there's still 4 kings in the deck and there's still 52 cards in the deck. And so that would again be 4 out of 52. And if you do 4 over 52 times 4 over 52, then you get 0.0059. But if I do it without replacement, and I do the probability the first one is a king and the second one is king, well, when I start, I have 4 kings and 52 cards. But once I draw the first one out, if it's a king, I only have 3 kings left, and I only have 51 cards left. So if I do 4 out of 52 multiplied by 3 out of 51, that gives me 0.0045. So that kind of shows you the difference between with and without replacement. Once I go through the problems on the Module 1 document and you see some of this practice, it will hopefully be a lot more clear if it isn't already.